Beyanova only by treatment, but this one has block and treatment. So we mentioned that we have to first get two information from our study. Or if we want to design a study, two things should come to our consideration first. One, how many treatments I have. Two, how many times I want to repeat these treatments. So number of treatments equal to how many, and number of replication equal to how many. These two information, you have to know about these two as the first things to know. So once you have this information, T times R will give you number of experimental units. So if you are able, let me accept this guy. If you are able to find this many experimental units uniform, you do this in CRD. But if we cannot find all the experimental units that we need uniform, we try to block them into uniform blocks. So within the block should be uniform, but between the block, if there is any variance or any difference, there is no problem. So last time we mentioned that, for example, we did an experiment and we said that, for example, this is our experimental area, and there is a kind of variation from here to here. This is our variation. Okay, direction of variation. Okay, let me write it again. No good. All right, we write it again. So this is our experimental area, and this is direction of variation. This variation should be a significant variation. For example, like humidity, like soil fertility. One side, for example, this side is low fertility, this side is high fertility. So whatever happens in this field, there should be a difference between this part, and this difference should be slowly reduced to go to the other part. So it should be something like this. So I say that, okay, this is the direction of my variation. I start from this one and gradually go to, from yellow, it goes slowly to become green. So therefore, this is the direction of my variation. If I say this is the direction of variation, this is wrong. Why? Because in this direction, everything is green. Everything is yellow. So I don't have variation from bottom to top. My variation is from left to right. So this is very important that you first understand which way is the direction of your variation. Then you have to block perpendicular to this direction. What does it mean? It means you cut it into uniform pieces. So imagine that if I do this, for example, I cut it from here to here, here to here, and here to here. So in this situation, you can see, okay, whatever is in the first block, I call it first block. And remember that we number block by Roman number. So this is block 2, this is block 3, and this is block 4. So I have 4 blocks. Inside block 1, everything is yellow. So everything's here is low fertility. I go to block 2, a little bit more fertility. Block 3, it is a fertile soil. Block 4, it is very fertile soil. So I could put all the units inside the block, meaning to say inside each block is uniform. So inside each block should be uniform. But if between this block and this block and this block and this block there is variation, there is no problem. This variation will be extracted using the block effect in the ANOVA table. This variation does not go to the error. This variation go to block. So in the source of variation, this variation will go to the block and make it, let me write it uniform here again. So that you remember, inside the block should be uniform, but if between the block 1 and block 2 or block 1 and block 3 there is any difference, there is no problem. But you have to remember that it is very important that inside the block you have to have uniformity. If inside the block I don't have uniformity, so I have a problem and my block became not significant, I will add more error to my experiment. So this is very important. But if I block like this, first my variation should be a significant variation. For example, if you remember in the laboratory that we did this week, RCBD, block became not effective. I mentioned that maybe the blocking was not done correctly. Maybe I block that in that experiment, blocking was in a wrong direction. Or sometimes maybe the blocking was correct, but the variation I used for a blocking was not a significant variation. For example, I thought the soil fertility is different, but the soil fertility was not different. I understand at the end of the study that my block is not significant. Therefore, I block by soil variation. I understand that soil variation is not a significant source of variation in this experimental area. So that's why if you want to do an experiment in one field, for example, field A in UPSI, there are students before you who did experiments there. If you can, it is good you go and find their thesis and look how they did blocking and their block became significant or not. So that's why in your thesis it is very good you put the experimental layout that if other students wants to go to see, okay, for example, a student A block from left to right, block became significant. So there is a variation in this land from left to right. So you also do the same blocking. But sometimes you block for one variation, you think this variation is significant, but at the end of the day, it became not significant and you feel and you will see that this variation is not significant. So if the block is significant, you gain precision. But if block is not significant, there are two situations can happen. Whether you didn't gain anything, surely you didn't gain anything, but you didn't lose anything also. So if block effective, I gain precision. If block is not effective, maybe I didn't gain anything, but also I didn't lose anything. And in the worst situation, block is ineffective and you lose precision. So that is the worst situation, that I did a lot of job to do blocking, my block became not significant, and it make my experimental error much bigger, that my treatment became non-significant. So I want the treatment to be significant. I want to find the differences among my treatments. So if my block is significant, I gain precision. If my block is not significant, but treatment is still significant, so I didn't lose anything. But if my block is not significant and I see my treatment also is not significant, in this situation, you should be very worried that you have done, you by blocking, you put a lot of error to your experiment and you couldn't find differences between the treatments. So this is what we have studied so far regarding to blocking. But now imagine that if I want to have one area next to this, what color I am? Okay, let's say this is another part. So here we mentioned this is fertility, it is fertile soil, it is fertile, and it is not fertile. So imagine here also same area. I have the same variation. Here is fertile and here is not fertile. But the situation is this: in this area, there is one water source here. No, I want to make it another color, maybe blue. Okay, there is a water source here. This is a water source. So this is water. So when I have water here, this area will be more moisture. This is wet soil, and this is dry soil. So now the question is this: which way I should block? If I block from top to bottom, I do it one time, top to bottom. Let me use red, that you understand red is blocking by fertility. So from up to bottom, if I block like this. So yes, in the block one, this area, all my soil is fertile. But the problem is this: inside the same block, some of the soil is wet, this is a wet area, this is wet, and this area, the humidity is very less. So this is a dry area. Again, I couldn't make the rule. The rule says inside a block should be uniform. So if I do opposite, if I block in this direction, for example, so what happened in this direction, I am taking care of my water because all of this area is wet and all of this area is dry. I could do that, no problem. But when I look at the other direction, this is one of my blocks. In this block, all the units are having a wet soil, so no problem. But at the same time, some of the units are fertile and some of the units have not fertile soil. So this direction of variation, I cannot take care. What happened here? Again, inside one block, there is no uniform experimental units. I could take care of the humidity, but I couldn't take care of fertility if I block from left to right. If I block from up to bottom, if I block in this direction, like this is my block, I take care of fertility. All of this soil is same fertility, this area fertility. But so fertility is uniform, but this area has more is wet and this area is dry. Again, inside one block, I do not have a uniform experimental units. So remember that the rule of blocking is that inside the block shouldn't be any variation. Inside the block, your experimental units should be uniform. Between the blocks, if there is any variation, no problem. But if inside the block there is a variation, that will make your experimental error bigger. So that you should really avoid. So if I want to do blocking for this situation, I am not able to use RCBD because RCBD can only take care of one direction of variation, like this example here. I have one direction of variation, fertile to not fertile. So I block perpendicular to my variation. So block 1 is inside, for example, is very fertile. Block 2 is a little bit less fertile. Block 3 is not fertile. Block 4 is very not fertile, for example. So, but inside my block, if this is my block here, inside this, all my units, if let's say this is my units, experimental units. So this one and this one and this one and this one, all of them are uniform. They have the same situation. All of them are not fertile soil. So in this way, RCBD is good. But when I go to this, but here I have two direction of variation. You can see one direction is from left to right, fertility to not fertile, and wet to dry. If this situation happens, RCBD is not a good design because any way you block, if I block based on fertility, again, I have problem with moisture. If I block based on moisture, I have problem with fertility. So there is no way to do RCBD. So what is the solution? The solution is a design, we call it Latin square design. Okay, this is actually a three-way classification or three-way ANOVA. Okay, I write classification. So what's happening in Latin square? In Latin square, I do blocking two times. Imagine that one times I block by fertility, one times I block based on humidity. I do blocking two times to solve this problem. So if this, and you see, maybe you say, okay, this very seldom happens. Yeah, maybe seldom this situation happen for you. But for the people who do experiment in greenhouse, this situation can happen very often because in greenhouses, maybe the light is different from one direction to another direction. Temperature, for example, your air condition, near to air condition is cooler than far from air condition. Or you have, for example, this machine make humidity maker. Near to humidity maker always is more humid and wet compared to far from the machine. So in greenhouse at the same time can be more than one variation available. So first you have to see that which variations are significant. After that, you try to do blocking. So that's why this design is very much useful for experiment in greenhouses. It's very common in greenhouses. So now we want to do two times blocking. One times we block from left to right, one times we block from up to bottom. So from left to right, meaning to say this is, okay, let me draw it again here. From left to right, I block like this. So we call it, so this is block 1, this is block 2, and this is block 3. So this is, I call it block by column. Okay, and then I block in the other direction, I call it block by row. And treatment. So I have three classification. CRD, only treatment. RCBD, block and treatment. In Latin square, I have blocking by row, blocking by column, and blocking and treatment. So that's why it is a three-way analysis, three-way classification. And remember, for making it simple, we do not call this block by. This one, we don't write it when we are writing ANOVA table. We just write column and row. So if I want to write an ANOVA table, for example, I write, for example, row, column, treatment, and error. This became my experimental variation, the source of variation. Row, column, treatment, and error. What is row? Row means blocking by row. This one. This is row. What is column? Blocking by column. Treatment is my treatments and experimental error. So remember that these two should be in one experiment, meaning to say I have to merge these two blocking, and here I have to have something like this. Again, this is my blocking by column and this is my blocking by row. So I have two direction I blocking. This one from here to here became blocking by row 1, blocking by row 2, and blocking by row 3. Okay, I call it row 1, row 2, and row 3. In this direction, we call it blocking by column. So I have, this is my column 1, column 2, and column 3. So, but for having this situation possible, meaning to say, so after that, in this situation, imagine that the variation is still the same. Here is one variation, fertility, and this is another variation, for example, humidity. Okay, so in this situation, block by row, you can see this one, block by row, this is row 1, row 2, row 3. I mean this one, sorry, why I put a star there. This one, block by row, this is my block number 1, number 2, and number 3. This one take care of humidity. So humidity in this situation is row. And blocking by column, column 1, column 2, column 3. In this situation, column take care of my fertility. So, but to be able to have such a design, there is one very important rule you need to remember. And this is number of row should be equal to number of column should be equal to number of treatments. So, means if I want to block 4 times by row, I have to have 4 column and 4 treatment. I cannot have 4 block, 3 treatment. It is not possible to do this kind of blocking. In this blocking, row should be equal to column, should be equal to treatment. So this rule has to be applicable. That's why when we are doing Latin square design, maybe the researcher only say one of them. the researcher says that, okay, a Latin square design was used to evaluate 5 treatments. So 5 treatments finish. I understand this experiment has 5 treatment, 5 column, and 5 row. Because any of these 3, I know the other one's also the same. So that's one thing to remember. And this is very important. If this is not true, your Latin square design is not correct. It is a wrong randomization. So again, we block 2 times. You imagine that you are doing RCBD 1 times from up to from top to bottom, 1 time from left to right. So what about the blocking? The blocking has the same rule, huh? Because last time in RCBD we mentioned that each block should be as big as having all treatments inside 1 times. Means here I have 4 treatments. So that's why my block has 4 experimental units. So here also the rule is applicable, meaning to say each treatment happens only once in each column and in each row. This is the 2 things you need to remember about what is this? This Latin square. First, number of row, column, and treatment should be equal. And second, each treatment happens only 1 times in each column and in each row. Meaning to say, if I put treatment A here, and here I cannot have A. Here cannot have A, here cannot have A. Here cannot have A, and here cannot have A. So you can see 1 times in each row and in each column. Because A happens 1 times here, in this row I cannot have any A. In this column also I cannot have any A. So this is the rules. If we do these rules, we are able at the end of the day to remove the variation of fertility by blocking in the source of variation for column, and I can remove the variation because of humidity by the source of variation called as row, if my blocking is correct. So let's say I want to make an experiment and I have 4 treatments. My treatment are 4. Let's, for the ease, we call it A, B, C, D. So, and this is my experimental area. So, first I understand that A, B, C, D, I have 4 treatments. Therefore, I have to block 4 times by column and 4 times by row. No need to know that, no need any extra information. I know I have 4 treatments. This is a Latin square design. Automatically, I understand I have to block 4 times by column and 4 times by row. So let's block it. Okay, this is block by column, and this is block by row. I don't like this last one. All right. So now, meaning to say A should happen 4 times, B should happen 4 times, C 4 times, and D 4 times. So now I need to do randomization. What is the rule of randomization? The rule of randomization is each treatment can only happen once in each row and in each column. You cannot repeat it. So what I do, for example, I start from treatment C here. I put C here. So here, here, and here I cannot put C. Here, here, and here I cannot put C. Correct? So where I want to put my second C, maybe I put the second C here. Here and here I cannot have C. Here and here I cannot have C. So maybe I put my third C here. Here and here cannot have C. So the only place left is here. This is my C. I randomize this. After that, I go and randomize, for example, A. So I put one A here, meaning to say here and here I cannot have A, here and here I cannot have A. So I go to the second place. Where can I put my A? Maybe I put my A here. Here and here, no A. Here and here, no A. I come here. I cannot put A here and here. These two already have A. So maybe only place left is here. I put my A here. And then therefore, here cannot have A, here cannot have A. And now, for the last four, for the last A, the only location left is here. So this is how I randomize the treatment A. Let's say now I want to randomize treatment B. So let's say I put my B here. So B cannot be here and cannot be here anymore. So where can I put my B? Here. Because this is 2A, A and C. Here I cannot put, and here this is the only situation I have A. So here and here I cannot put B. They are already full. Here, here and here also I cannot put B because I have one here. I come to this one. In this one, for example, I put a B here. Here and here cannot put B. I put my last B here. So B, 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 and B. And the last one left is, let me change the color to this, D. If I put my D here, oh, this is again red. Oh, okay, let me do it. If I put my D here, so you can see first column, this one, C1, have A, B, C, D. And last row, this is row 4, have A, B, C, D. Okay, good. I come here. If I put a D here, okay, my column 2 has A, B, C, D. And my row 3, this is row 3, this is column 2. My row 3 also has A, B, C, and D. I come to the column 3, I have A, B, C, I put my D here. So this one is A, B, C, D, and column is A, B, C, D, correct? And the last one will be here. This is C4 and row 1. So column 4, A, B, C, D, and row 1, A, B, C, D. Okay. So this is how we do randomization in Latin square. Up to 4 or maybe 5 treatment is easy to randomize manually. But if you have 7 treatment, it is very difficult to do it manually. We can write a program in the SAS to say to SAS how many treatments I want and ask SAS to randomize for me. SAS will give me a table like this that I know where should I put my treatments. If I do this randomization is correct, and I'm able to do this experiment in Latin square analysis. So if I want to analyze this one in Latin square, what is my source of variation? I have a source of variation, degrees of freedom. Again, I need to have SS, MS and F. Title of ANOVA is always same. So what is my source of variation? My source of variation is row, means blocking by row, column, means blocking by column. I have treatment, my treatment, error, and finally I have the total. So this is my source of variation. This row means blocking by row. Column means blocking by column. So that's why we do not use the word block by. It is understood. That's why we call it just row column. Means block by row, block by column, treatment, error, and total. When I want to write my DF, this DF is the easiest DF. Remember that row, column, and treatment are same. They have the same number. So I can put, for example, row is R minus 1. Column is column minus 1. Treatment is treatment minus 1. Okay, so row minus 1, column minus 1, treatment minus 1. But the answer to all of this is, in this example, 3. Why? Because R is 3, C is 3, and T also is 3. So you can write like this, but because R, C, and T are all same, the people write it all using only R. We use only the R. So we say that this is R minus 1, R minus 1, R minus 1. Error is R minus 1, R minus 2, and the total is R squared minus 1. So just to make it easier to remember, we use R for all of the sources. Why? Because you can use C, you can use T, up to you. Because R, C, and T are same. Number of row, column, and treatment are same. So just for the ease of remembering, we call it R minus 1, R minus 1, R minus 1. Error is R minus 1 times R minus 2, and total is R squared minus 1. So in this example that we have here, this 3 will be, all became 3, 3, and 3. 4 minus 1, correct? And this is also 3. R minus 1, R minus 2 is how much? R minus 1 is 3, R minus 2 is 2. 3 times 2 equal to 6. And the total is R square, means 4 times 4 is 16, minus 1 is 15. So you can see in this example, I have 16 experimental units. Okay, 4 by 4, 16. Therefore, 16 minus 1 became 15. If I am right, the total of this should be also 15. So 3 plus 3 plus 3 is 9. 9 and 6 became 15. So my calculation is correct. Then I calculate my MS, SS. After that, I calculate my, I write this part again because no space. Okay, this is the F. Let's say I write my SS here, MS and F. So I have, I will calculate SS for row, SS for column, SS for treatment, and SS for error. SS divided by DF give me variance of MS for row, MS for column, MS for treatment, and MS for error. And lastly, I need to calculate here 3F. F for row is MS, row divided by MS error. For column is MS, column divided by MS error. for treatment is MS treatment divided by MS error. So here I have 3 F. First one will tell to me blocking by row was significant or not. Second one tell to me blocking by column was significant or not. Last one tell to me my treatments are significant or not. So this is very easy on our table. What you need to remember these 2 rules. These 2 rules are very, very important. That the number of row, column, and treatment in Latin square is always equal. You cannot have 5 treatments and 4 block. It's not possible. If you have 5 treatment, you have to have 5 row and 5 column. And each treatment happens only 1 times in each column and 1 times in each row. That we did randomization here. Here, any color of this treatment, red, blue, black, whatever, you see only repeated 1 times in column and 1 times in row. For example, A here. A here, you can see this is column 1. I have only 1 A. There is no other A in column 1. This is row 2. In row 2 also, only I have 1 A. There is no A in this direction and in this direction. So this rule has to be applied for all the 4 treatments that I have. Okay, so what are the problems with this Latin square? The first problem with this Latin square is this one. That is one of the limitations. Why? Because I cannot have too many treatments. If I have too many treatments, my experimental area became very big. For example, you imagine you want to have 10 treatments. Okay, my treatment equal to 10. In RCBD, in CRD and RCBD, you are able to select any replication you want. So I select here all equal to 3. Here I select, for example, R equal to 4. Just different numbers to see. So here I have 30 units. Here I have 40 units, which is still big. But let's say this is the situation. But when I want to do Latin square, I keep the same number of here that you don't think CRD is smaller than RCBD. No. These 2, I keep same number of replication, 30 and 30. But when I go to Latin square, it is not my choice to have 3 replication. I cannot do that. Why? Because my treatment is already 10. I have to, this is have to, R should be equal to 10. Therefore, I have to have 100 units. So this is the problem. Make my design very big. If I want to run 10 treatments in CRD and RCBD, my treatment is too many. I reduce the number of replication. I don't run 4 or 5 replication. I run 3 replication. So my unit became 30, it's still manageable. But in Latin square, if I want to test 10 treatments, I have to repeat it 10 times. Therefore, my experimental area became 100 experimental units. It is too big. So this is the problem. Okay, and now let's say we calculate for here. I say this is the treatment. This is number of experimental unit, and this is degrees of freedom for error. Okay, we see what happened. If 2 treatment cannot, 2 is t-test and z-test. You have to start from 3. If I have 3 treatments, automatically 3 to the power of 2 became 9. I have 9 experimental units. How much is my degrees of freedom error? Remember that this is R or T, R minus 1, R minus 2. So 3 minus 1 became 2, 3 minus 2 became 1, 1 times 2 is 2. I have 4 treatments. My experimental unit became 16. How much is my degrees of freedom? 3 times 2, 6. I have 5 treatments, 25. How much is my unit? Became 5, huh? 4 times 3, 12. 6 treatments, 64. You can see I add 1 treatment, 5 became 6. See how big the difference is this. So how much is this? No, not 64. Why 64? How much?
36.
36. Okay, good. I know you are listening. But again, see, 1 treatment I apply, I have to add 11 units. Just for having 1 more treatment, I have to add 11 units. So, will be 5 times 4, 20. 7. 7 should be 7 times 7, 42. 42. How many experimental unit will be 6 times 5, 30. I go 8.
Dr. 49.
Pardon?
7 treatment should be 49, right?
49, sorry. 7 times 7, 49. Yeah, correct. Thank you. 49. How much is my experimental error? 30. R minus 1 became 6. R minus 2 became 5. 6 times 5, 30. Okay. 8 times 8, 64. So will be 7 times 6. 42 is here. 7 times 6. Okay, I just continue until 10. 9, I will have how many? 9 times 9, 82. So will be 8 times 7, 56, and 10. I have 100 units, and will be 9 times 8, 72. Okay, so now if you look at this, you can see that this experiment for Latin square until 7 is manageable. It's still manageable. But more than this is too big. Okay. And if I want to do experiment here, my degrees of freedom for error is 2. So this is too small DFE. This is too big, let's say I call it too many, not too big. Too many experimental units. So if I go more than 7, if I am around 2 or 3 treatments, 4 treatments, you can see my degrees of freedom for the error is very small. For example, 3 treatment, degrees of freedom for error is 2. So when degrees of freedom for the error is small, automatically variance of error became big, because variance is MS. MS is calculated based on SS divided by DF. When my DF of error is very small, my variance of error became big. So That's why most of the papers that they do Latin square are from this three. Maybe I also sometimes see this 7. Okay, but 7 is still 49 experimental units you have to have. Okay, the sweet spot is this 3. 4, 5, and 6 treatments. Degrees of freedom is 6. 6 also is still not that big. 6, 12, and 20. So not that bad. So that's why this is the limitations in Latin square. Latin square, the problem is you are not able to select how many replications you want. You have to have as many replication as number of treatments. If you have 5 treatments, you have to repeat it 5 times. So this is the main problem with Latin square. So, but if you have to do this, meaning to say, especially in greenhouse experiments, that it is very possible you have more than one direction of variation. So in that experiment, we will have, we have to do Latin square. So, okay, for example, if my study is here, this is my greenhouse, okay, this is the door, I go inside the greenhouse. So, okay, let's say there is one air can here, this is air conditioner, so this area always is cool, this area is a little bit warm. Okay, and imagine that this side is wall, this is a wall, and this side is glass. This one and this one is glass. So therefore here is darker, here is lighter. So the problem here is based on light. Or sometimes they put air conditioner here, they put the machine who make a humidizer here. So humidity became in this direction. Again, I have 2 directions. So in greenhouse, it is possible that we have 2 direction of variation. And sometimes in the field also can happen fertility and, for example, moisture. So that can happen. Can I have variation in 3 directions? So here are 2 directions, correct? This is one direction and this is another direction. This direction is temperature. This direction is light. Can I have another direction of variation? Where is the third one? How can I have third? Remember that we live in a 3-dimension world, so it is possible to have 3. Okay, how it is possible? You know that in 3-dimension world, I have x and y, and I have also height, which we call it z, correct? So imagine that, you know that now we have some greenhouses that they have vertical farming. I'm sure you heard about vertical farming, that they have many trays above each other. This is one here, one here, one here. They go up like this. So this is planting. They plant here, after that here, 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 here. They plant like this. They call it vertical farming. So instead of planting only on the surface, they plant on the tray and put the tray above each other. So if this situation happens, yes, you can have 3 dimension of variation. Okay, so you know that always temperature, the cool temperature remains on the bottom. Top area is more warm compared to the low area. So maybe there is a situation like this can happen. Okay, but very, very seldom, only maybe in this vertical farming. But if this happens to you, the only way you can solve this, there is one design that I'm not going to teach you, and we call it replicated squares. Instead of Latin squares, we call it replicated Latin square. So replicated Latin square. Replicated Latin square. Okay, what is the replicated Latin square? Means in each tray, I do one Latin square. For example, I want to do 5 treatments. So here in the tray number 1, this area, I have to have 5 times 25 units. In the second tray, 25 units. How many tray I have to have? Here, no need to have exactly 5 tray. You can have any number you want. Okay, maybe I want to keep it 3. So in this way, there will be a new source of variation that we put it before row, and we call it a square. So that calculation is different. Just one thing from me, that if you go in a modern form and you see sometimes at the bottom of this vertical forming, you have less or more fruit. Up there, you have less fruit. So yes, you can have a design like this. You say, okay, one direction, for example, is temperature. Another direction is humidity. Because light cannot be a problem here, because they use LED and all of them have the same amount of light here. So the light cannot be the problem here. So maybe humidity and temperature. After that, you see, for example, lower tray has more yield compared to the upper tray. So it's possible that you design an experiment, we call it replicated Latin square. So, and find what is which variation is significant and how it is. So, because you know that now in Denmark, for example, I read in the news 2-3 days ago that in Denmark they opened one vertical farming in very small area, but they can produce 1,000 metric ton of vegetable per year. Means 1 million kg of vegetables like cabbage and these things in a very small area. So this vertical farming is a way for the future, because we don't have that much of land left, and if we want to clean the jungles to make the farm, we will kill ourselves, because there is not enough. The weather will be very bad, because the jungles are the lungs for the earth. They absorb carbon dioxide and release oxygen. So that's why now these advanced countries, they are going to this kind of farming. They are going to vertical farming. They make the farming like a modern activity. So these things also you can also think about this. All right, this is all about Latin square. Let me show you some of the slides that we have very fast. So Latin square, here we have two-way removal of experimental error. Two-way removal of experimental error. So what is the two-way removal? By column and by row. Okay, before I come here, wait. How can I go out? Okay, one thing I want to do, and that's one small comparison. I want to do one small comparison between these 3 designs. Okay, to be able to do comparison, I will take the number of treatment equal to 4, number of replication also equal to 4, just to be able to compare CRD, RCBD, and Latin square together. Okay, if I have CRD, I only write source of variation and degrees of freedom. Okay, if I have my CRD, source of variation is treatment and error. Total to this plus this became total. So treatment, degrees of freedom will be T minus 1, which is 3. Error will be how much? T into R minus 1. T is 3. No, sorry, T is 4. 4 times R minus 1. 4 times 3, 12. T into R minus 1, 12. So you see this is 4. This is 4 minus 1, 3. 4 times 3, 12. All right. This is our CRD. When I go to RCBD, I add another things, my source of variation and my degrees of freedom. I have a new things, we call it block. Okay, just to be easier later to conclude, I want to keep treatment up there always. Okay, so I keep treatment here. I have treatment and block and error. Normally we write block treatment error, but now just because I want to do comparison, I want to keep the treatment on top for all the design. So, and I have total. Okay, here total will be RT minus 1, which is 15. So for RCBD, this one is T minus 1, again, this is 3. Block is R minus 1, is still again 3. And error is R minus T minus 1 into R minus 1. This is 9. So you can see what is happening. The treatment is same. You can see the treatment here is 3 and here is 3. So we have no problem with treatment. But what happened? This 12 divided into 2 parts became 3 and 9. So this 12 became 3 and 9. You can see this one and this one. So one-way experimental error removal only by block. So what I did, I get 3 degrees of freedom from the error of CRD and give it to the new source of variation in the name of block. And I hope that my block became significant. Then I go to Latin square. So let me again keep the treatment up here. After that, I have block by row, by column, error, and also total. Okay, this total also will be RT minus 1 equal to 15. So treatment, row, column, error, all of them are R minus 1. R minus 1, R minus 1, R minus 1, R minus 1, R minus 2. Okay, so here 4 minus 1, this is 3, 3, 3, and R minus 1, R minus 2 is how much? 3 times 2, 6. So again, you can see that my treatment is still 3. All the design, the treatment is 3. But you can see here now, the experimental error became 6 degrees of freedom compared to this 12. So what happened? This one and this one. Okay, if I want to show from RCBD, in RCBD, this 9 go to 3 go here, 6 go here. This block is still this one. So can you see Any blocking I add, I'm losing degrees of freedom for error. CRD, my degrees of freedom for the error is 12. Same number of treatment and replication. Huh? My total here is also r squared minus 1. 16 minus 1, this is r squared minus 1 is 15. So always 15, my total. I have 15 degrees of freedom of total, means my experimental units always are 16. In CRD, I have 12 degrees of freedom. That's why one of the advantages of CRD was maximum degrees of freedom for error, which is good. So 12. When I go to RCBD, from that 12, I send 3 to a new source of variation in the name of block, and remaining 9 will go to the error. And I hope that by doing this, I can have a significant block, effective block. When I go to Latin square, these 12, 3 of them I give blocking by row, another 3 I give blocking by column, and whatever left, which is 6, will remains to the error. So you can see that's why we call it in the Latin square, degrees of freedom for the error became very small. So therefore, you shouldn't use Latin square unless necessary. Okay, this is very important. Do not think that, oh, Latin square is a more complicated and better design from RCBD. No. Latin square disadvantages is here. You lose a lot of degrees of freedom for the error. Therefore, if your row and column is not significant, what happens? These two are not significant. Most probably, you lose precision and cannot find treatment significant variation. Why? Because degrees of freedom for error is very small. SS divided by 6 will give you a big MS. Here, SS divided by 12. Here, SS divided by 9. Here, divided by 6. Of course, this one became bigger. So that's, you can see, Latin square is not a good design in the form of the degrees of freedom for error. Therefore, this should be our last choice. If I can do CRD, I have to use CRD, the best design. All experimental units uniform. If I cannot do it, I try to do blocking 1 times, do RCBD. If still I have variation inside the block, and I have to do 2 blocking, I have to go to Latin square. So step by step, you decide. Do not say, okay, I do a Latin square because the name is very fancy and a lot of things inside. So don't do this. This one, we only use it in a certain situation. And the disadvantage of this design is replication and treatment should be same, and error has very small degrees of freedom for error compared to other design. Compared to other design, this one has very small degrees of freedom for error. So this is also the comparison between these 3 designs. So let's continue here. So in Latin square, the error, experimental error, I remove 2 things from experimental error. One, blocking by row, and another blocking by column. We do this normally in a small experiment. Why? Because if it is a big experiment, I have to have too many experimental units. When I have many experimental units, I put error to my experiment. So it is not advisable to have a big experiment. So, and last I mentioned again, this is 3-way ANOVA or 3-way classification of factors and grouping done by treatment, blocking by row and blocking by column. This is important. Every treatment occurs once in each column and each row that I show you already. Now to go next slide. No. Okay, about randomization, I just did for you randomization, and you can see example here, moisture and fertility, I put again, and you can see that the color, for example, red in column 1 is only 1 times repeated, in last row also 1 times repeated. This is important. So linear additive model. Linear additive model, last time I told you, this is the same part and the error always exists. So each observation should be equal to the population mean plus the effect of row, effect of column, and effect of treatment in this case. Whatever also left, we call it the error. So if I want to do analysis in SAS, for example, I will have to write these 3 in my model because error is whatever left, and this part also, I don't know how much is mu, so no need to have this part. The middle one I have to put in the model in the SAS to be able to analyze. So okay, this one, why I didn't put SSC here? It's okay, this is SSC. So the analysis of variance, I show you, you have 3F, row divide by error, I check, column divide by error, I check, treatment divide by error, I check. So this is this, and I use R minus 1 for R. But you can say this one is C minus 1, this one is T minus 1, this one is R minus 1 in T minus 2. Whatever you use R, T, C, same, because they are all same number. So it doesn't matter which one to use. Just for the ease of remembering, we use only R in degrees of freedom for error in Latin square. So R minus 1, R minus 1, R minus 1, R minus 1, R minus 2, R squared minus 1. So about the calculations also, what we do, we calculate CF, we calculate SS total, same. We calculate SS treatment, same, means all of the what is this? I have, for example, 4 treatment and 4 replication. So I have 4 treatments A. So all of these 4 treatments A total together to the power of 2. After that, treatment B, 4 of them total together to the power of 2. So exactly what we did before. Then I have a SS for row. How I do? This is exactly like calculation for block. So row number 1 total to the power of 2. Row number 2 total to the power of 2. Row number 3 total to power of 2 until the last row. Summation of all of this power of 2 divided by R minus CF. What about the SSC? For the column, same story. This times I get the total of each column. Column 1 total to the power of 2. Column 2 total to the power of 2 until the last column. Then I total all of these power of 2 divided by R minus CF, and my error is SS total minus SS treatment minus SS row and minus SS column. So, and this is what I did for comparison, that you can see here, the comparison. Okay, this is the error. Okay, this is error. Sometimes in some papers for RCBD, they write block treatment, block times treatment. This block times treatment, we call it, this is the error, so don't be confused. Some of the people write it block treatment, block times treatment. Error in RCBD is block cross-classified with treatment. This cross, we call it cross-classified. Block cross-classified into treatment. That's why it is R minus 1, T minus 1. So if you see something like this, This is error for RCBD. Okay, I did now this comparison also we did. This one you see, when the number of treatment is small, my degrees of freedom, error degrees of freedom are very small. Then my number of treatment became big, my experimental units became very big. So you can see 7 became 49. Here I put until 36, but sometimes also 7 treatment I have seen seldom. But the sweet spot is this one. This is the sweet spot to do Latin square. 4, 5, and 6 treatment. One of this. This is the sweet spot of Latin square. Less than this, it is too small degrees of freedom for error. Bigger than this is too many experimental units in the study. Okay, this is what I just mentioned. So advantages, MSE is reduced if blocking is effective both directions. Means if row is significant, column is significant, my MS of error became significantly smaller. ANOVA is very straightforward, may evaluate the effect of possible gradients. What does it mean? Meaning to say, in CRD, I only can talk about treatment. In RCBD, I can talk about the treatment and that variation I block with. For example, if this is blocking by fertility, I can talk about the treatment and also fertility of my experimental area. In Latin square, you can talk about the treatment, you can talk about the blocking by row, you can talk about blocking by column. So you have more source to talk about. So these are the possible advantages. But the disadvantages is if blocking is ineffective in either or both direction, MSE is not reduced. This sacrifice precision. MSE and all tests of significance are invalid if row and column interact. Okay, this one I forgot to say to you what this means. So meaning to say your row and column, that variation by row, variation by column. In this example, for example, we show, go back, this card. Let me go back here. In the example that we did, for example here, so you can see humidity and fertility got nothing to do together. One soil can be very fertile and dry. One soil can be very wet but not fertile. So these two have no correlation. But imagine that instead of humidity, I put weed density. Okay, I block based on width density. So you can see width density and fertility interact together. What does it mean? Means if I have more fertility, I have more width. If I have less fertility, I have less width. So these two things have correlation together. So it doesn't mean that both of them go up together, down together. If one of them go up, the other one go up or down, and one of them go down, the other one go, okay, can be like this, huh? This one go up, this one go up, or this one go down, this one go down. This can be, we call it positive correlation. This is positive correlation. What is the negative correlation? The negative correlation is this one go up. Where should I put it? Okay, I put it here. Fertility go up, then this one go down. Fertility go down, this one go up. This is negative correlation. But the thing is, fertility and width density are related together. When it is more fertile, of course I have more width. So these two, column and row, are related together. They interact together. This can cause all of your Latin square to be wrong. This happens to one student at the UPM, PhD students, and I was in a Viva at that day. The PhD students has made a mistake like this, and he was given to resubmit, not reviva. Resubmit means you have to go and do some experiment again, write the thesis, submit for again for evaluation. That is the worst things. So because in Viva we have different, for example, accepted by correction. After that, reviva means your presentation was not good or some of your analysis was not correct. You have to go and do analysis, but your experiment is correct, your analysis is not correct, so you come back and present again. But if your experiment is wrong, they give you resubmit, means you have to go and do experiment again and come back. Or if it is very worse, that they reject you. So this caused one PhD student, just this point, caused one PhD student to resubmit the thesis. Because forget about this rule, that in Latin square, columns and row must not interact together. They should be different, no relation. They shouldn't have any relation. So why? Because we cannot calculate real interaction between columns and rows. Therefore, we cannot access this. Therefore, we cannot use. So this is very important. So they have to make sure or assume that they are all independent. Means column and row got nothing together. Anything can happen between them. It is not related to each other. And another why, it is one of the reasons why it is limited use inside the field. Because in field, many things are related together, like more fertile, more weeds, less fertile, less weed. So sometimes in the field, we don't use Latin square that often. I told you, Latin square is very good design for laboratory, for greenhouse use. And size limitation that I mentioned, that because R, T, and C should be equal. So too small degrees of freedom for error, or too many experimental units. Okay, this relative efficiency, no need to discuss with you, and this is finished. All right, so this is the last experimental error we discussed. So the experimental error we discussed in this class are these three: CRD, RCBD, and Latin square. Okay, most of the time you use these two. This one you seldom use. So in next lecture, that which is important, we want to use it is not a design, it is an arrangement of treatment. Okay, see, imagine that I want to have two different treatments in one study. Okay, so what we want to discuss is we want to have not two treatments, two different type of treatment. For example, in one study, I cannot put, for example, my treatments are variety 1, variety 2, variety 3, fertilizer 1, fertilizer 2. I cannot do this. I say, okay, I have 5 treatments, 3 variety and 2 fertilizer, 5 treatments. So this is totally, and I use CRD or RCBD. This is totally wrong. Why? Because you cannot say variety is better than fertilizer or fertilizer is better than variety. They are two different things. You cannot say, oh, my car is better than your house. You cannot compare. Car is something, house is another thing. So we can only compare variety together, not fertilizer together. So meaning to say I have to do one experiment for variety, one experiment for fertilizer. But is it possible I do one experiment and have both of these together? Yes. This is what we call it factorial arrangement. Factorial arrangement I only discuss for these two. For Latin square, you don't need to use factorial in this class. Will be complicated. But these two are very easy. We will discuss that. If I have more than one kind of treatment, meaning to say in one study, I want to have different type of treatments, like I want to have variety and fertilizer. I want to have, for example, what is this? Nitrogen and phosphorus. I cannot say nitrogen is better than phosphorus because they are two different things. So maybe I want to have 3 level of nitrogen, 5 level of phosphorus. I want to understand what is the best nitrogen and what is the best phosphorus. I have to do two separate experiments, but is it possible to put these two experiments together in one? That is what we call it as a factorial. So this is what we discussed in next lecture, and that is the last experimental design. Okay, so now, is there any question up to now?
No, doctor, understood.
All right. So in the laboratory, I will give you the laboratory that you do it in the, I will send it this time inside WhatsApp because in my group, I don't know why I put it there, why it doesn't appear. I cannot find it myself. So I put it there. So please spend some time to calculate this Latin square one. Because if you calculate Latin square, you are already able to calculate RCBD and CRD. Latin square has calculations of CRD and RCBD inside. So if you are able to calculate Latin square yourself without any help, you have no problem in calculation of ANOVA. So it is a good test for yourself. Then today, when we have a little bit time, maybe I just talk a little bit about your assignments. Okay, so who is group one? Just the leader, huh? Who is group one leader? Okay, Hafiz, what is your title? Cluster analysis. Okay, did you understand your group? Did you find anything to understand what is cluster analysis? Okay. What is good? Okay. So I understand you didn't understand what to do. Okay. So we need to discuss about cluster analysis. Okay. Who is group two? Yes. Don't worry. I will explain now. I just want to know what title we have. I forgot. So what is group two?
Me, sir.
Okay. Farida. Farida, what is your title?
Factor analysis.
Factor analysis. Okay, very good. Did you study anything about this one yet?
From what I read, factor analysis is the observations of analysis that we do, like something that we observe.
All right, we observe.
Yes.
Okay. So now after this, you really understand what is the difference between you go and read from a book or journal paper or internet, or the way I explain to you, how much my explanation makes life easier for you. Okay. Why? Because learning a statistic from book is very difficult. Needs a lot of time and efforts. So you will, what is this? Yes,
Sorry, my group is Monova.
Manova. Okay, you also don't know what is your title. Very good. So Manova. Manova means multivariate analysis of variance. Correct? I put the title there. Manova is a stand for multivariate analysis of variance. So what is Manova?
I'm mistake. My
Title. Okay, no problem. I will explain.
sorry, sir.
So cluster and Manova. Group number 4, 3, sorry. Who is group 3? So one of the groups should be factor analysis. Who is factor analysis group? Amazing, huh? You don't know what group are you? So
Our group, sir.
your group, huh? Anis. Anis, your group is factor analysis.
Yes, sir.
All right. So have you studied anything so far or no? You cannot understand yet.
Sorry, sir. We don't understand yet.
Okay, no problem, no problem. This is I still have time. Okay, so who is next group?
Doctor, it's our group.
So what is your title, Sinha?
Principal component analysis.
Okay, PCA. Did you understand what is PCA? Anything?
No, doctor, we haven't discussed yet.
Okay, very good. Well done.
I just download few articles, but not read it.
All right. So who is the last? Is there any other things left? So this is the titles we have: Manova, cluster analysis. What else? Factor analysis.
The last one is
PCA.
regression analysis and qualitative and quantitative.
Okay, who is regression analysis?
I think it's our group, sir.
Okay, so please don't think, sir. Get sure that what title is your group, and you have to start doing your assignment because you have to understand what is these techniques. All of these techniques are very common techniques in the statistics. Okay, so let's say all of the techniques that I mentioned, you mentioned now, or let me. I open one. I don't want to mix. That page. All right. So all of the things you discuss now come until some things we call it multivariate analysis. Okay. Why is it very big? Okay, multivariate. Against univariate. What is univariate? Univariate is what we are doing now, ANOVA, analysis of variance. So t-test, z-test, they are univariate. What does it mean univariate? Means you talk about one variable at a time. One variable at a time. So I run one study in, for example, I do one study on, let's say, corn, for example. I want to test for fertilizer in corn. I apply the treatments, I do my analysis, but when I go to ANOVA, I do analysis one by one for each of my traits. I do one ANOVA for yield. I do one ANOVA for plant height. I do one ANOVA for ear size. So one trait or one variable at the time. Only we speak about one thing. So this is univariate. Multivariate means that you talk about it having more than one variable. So in corn, for example, I have yield, days to tasseling, days to maturity. I have, for example, ear diameter, ear length. So when I do ANOVA, one of them say yield variety 1 is the best. Days to maturity, variety 3 is the best. Very fast will be ready. The days to maturity is very low. When I go to diameter, I will like to have a big cob. For example, variety number 2 is good. So for yield, number 1 is good. For maturity, number 3 is good. For cup diameter, number 2 is good. So at the end, which is good? What variety I have to plant? You want to say to other people. If you want good yield, you use only variety 1. But if I want to have good yield and good diameter and also fast maturity, what variety? Univariate cannot answer these questions. We have to go to the analysis that we call it multivariate. So in multivariate analysis, I have more than one variable at the same time. That's why now the MANOVA come to the picture, multivariate analysis of variance. So in multivariate analysis of variance, this is ANOVA, one by one. One ANOVA table for yield, one ANOVA table for plant height, one ANOVA table for cup diameter, so on and so forth. But in MANOVA, which is multivariate, here I do one analysis, one table, one ANOVA table, but for everything together. Meaning to say, in this analysis, I consider yield, plant height, diameter of the cup, maturity, everything I measure in this experiment, I put it inside this, and I can say what is the best variety overall, which treatment is the best, not for one variable, for all variables. So this is very important analysis. Why you cannot see this? Because not many people know how to apply this. So MANOVA is when you do ANOVA for more than one variable or trait. When I have more than one variable, meaning to say yield and maturity together became MANOVA. But what we do, for example, in one study, I collected 10 variables. So I run all of 10 together to understand what is the best treatment for everything, not only for yield, not only for plant height, not only for maturity, for everything. Everything together, which variety has the best, meaning to say it has everything at high level, maybe not highest yield, but it has high yield, days to maturity is also short, plant height also short, cob ear characteristics also very good. So not the best for every, but the best overall. So that's what we call it, MANOVA or multivariate analysis of variance. So in multivariate analysis of variance, what you have to do is that you shouldn't have one variable. If you have only one variable, you cannot do MANOVA. For example, in the laboratory I give to you, inside the laboratory, we only have one trait, grain yield, for example. So here I cannot do MANOVA because I have only one trait or one variable I collected. So if I cannot do for MANOVA, I have to have more than one variable. So in the real studies also, you don't collect only one thing. You collect different variables or traits. We call it traits in agriculture. In a statistic, we call it variables. But in agriculture, we call it traits. We get more than one trait. So MANOVA is analysis of everything together. What is the best treatment? If I consider everything I collected together. So this is what MANOVA means. So you can go, and it has also a table like ANOVA, and you can go, now you understand what is MANOVA, the basic of MANOVA, you can go and start to gather information about this. So what you need to know, maybe you have a little bit of introduction. After that, you can have some kind of materials and methods. The best I offer to you is you try to have data and analyze the data using MANOVA. For example, you can use it, what is this, by software, or maybe you can find example from internet, but you have to explain step by step what happened and get conclusion. That is the best type of assignment. But you have introduction, you talk about this a little bit, when we use MANOVA, why we need to use MANOVA, what is the differences between this one and ANOVA. And after that, if you have a data, you analyze the data and you get a conclusion from this data. This is very good. And I don't want you to calculate manually. The problem with these statistics like this, MANOVA or cluster analysis or PCA, is that they are very difficult to be calculated by hands. There are a lot of calculations. So nobody calculates these things by hand. MANOVA, nobody calculate by hand. You have to use a software. So you can use SPSS, you can use SAS. There are softwares that you can use to analyze this. If you can find an example for how we analyze this, for example, you find the SAS code, how we analyze MANOVA in SAS. Or you have a data and you have a result from SPSS. You explain the result. Okay, here what does it mean? Here what does it mean? At the end, what is the conclusion? Okay, so this is about MANOVA. So MANOVA is very similar to ANOVA, but I don't do it for one trait. I consider every traits together and do one analysis. So if I have collected 10 traits, I have 10 ANOVA table, but I have one MANOVA table, all the 10 together. So this is what we call it multivariate analysis of variance, that we have more than one variable or traits to analyze at the same time. So this is about MANOVA. Then we discuss about these three: cluster analysis, principal component analysis, that I call it PCA, and factor analysis. So these three things are very, very similar. Okay, this cluster analysis, factor analysis, and PCA are very similar. Okay, when we do these things, when you want to group your individuals, okay, into different groups based on their characteristics. Just imagine that I come and get your data. For example, I come and get your height, your hair color, your eye color, your, I don't know, any traits I can. What is your shoe size? How long is your hand? I don't know. How much do you weigh, for everybody in the class? And now I want to say that, okay, these people are very similar. These 5 people are very similar. these 6 people are very similar. I want to divide them into distinct groups. So in this case, we use one of these 3 techniques. We use cluster analysis, PCA, and factor analysis. Okay, so what I want to do, I want to divide my samples into distinct group. What is distinct group? Means the group that they are different from each other. I want to divide them into different groups that they are different from each other. Okay, for example, I do one experiment on genotypes or variety. I call it variety, easier for you to understand. For example, I have variety I have variety 1 until variety 10. Okay, and from these varieties, I start to collect some data. For example, I collect yield, I collect days to maturity, I collect plant height, I collect fruit number, I collect, for example, fruit size, and whatever. So each of these things are one variables. This is one variable, this is one variable, so on and so forth. So if I want to talk about which variety is the best for yield, I use ANOVA. If I want to say which variety is good for the fruit size, has the biggest fruit size, I use ANOVA because I'm talking about one variable at a time. So I can do this by ANOVA. If I want to say which variety is the best overall, means the variety with highest everything, I have to use MANOVA. In MANOVA analysis, yield, day to maturity, plant height, fruit number, and fruit size, all of them consider one data. And we use it to calculate MANOVA. So this is MANOVA. But how if I want to group my varieties, for example, I want to group them into high performance and fast maturity. Okay, so actually when we start to do grouping, we don't know how many groups we will have at the end. What I want to do, I want to group my varieties to see how many groups they are. All of them are in one group, or I can divide them in different groups. So maybe the result will be 3 groups, for example, 1 group, 2 group, and 3 groups. So in group 1, maybe variety 1, variety 5. Here maybe became variety 2, variety 3, variety 4, 5, and variety 6, variety 7, variety 8, variety 9, and variety 10 became in this group. So what happened? I say that variety 1 and variety 5 are very similar. For what? For all of the things, not for yield or pH or size. For everything together, these 2 varieties or 2 samples are very similar. These 3 varieties are very similar. These 5 varieties are very similar. So you can see there are different numbers of variety in each group. This action, we can do it by cluster analysis, we can do it by factor analysis, and we can do it by principal component analysis. They are doing the same story, but in different ways. In cluster analysis, what we do, we calculate, there are different type of clustering. So the technique for clustering, there are different methods. For example, sometimes we say to the software how many groups we want. For example, somebody give me 10 variety, tell to me some of them are imported, some of them are local. Which one is imported, which one is local? I don't know. This is mixed. You find it. So in this way, I say to software, I want to divide this 10 variety into 2 groups. So the cluster will divide it into 2 groups. No. So this is one principle. Another principle is when I don't know how many groups, the software tells to me how many groups at the end. So, and most of the time, the cluster will be something like this. If I want to write a cluster for this one, for example, I will write V1 and V5. For example, these two are like this. After that, go to V2, V3, and V4. For example, these two are very near. After that, with this one will be connected to this one and go up, and the other 5 will be V6, V7. Imagine I put 8 only. Okay, maybe this one and this one collect together, plus this one comes, and all of these collect to this, like this. This is a cluster analysis. So you can see that in this cluster analysis, I have 2 main groups. One main group, you can see, one main group is this, one main group is this. But in this main group, I have 2 subgroups. This is subgroup 1, this is subgroup 2. This is how a cluster analysis can help us. It is very useful for a study of DNA studies, that you get a DNA sample from different plants, and after that wants to put them, you know that because there is things that, for example, they say do not marry your cousin. Why? Because you and your cousin have similar genes. So maybe a bad gene from you and a bad gene from your wife go to your child at the same time, and your child became syndrome Down. So this can also happen in other things, in plants, in animals. So I want to produce, for example, a good seed. I have to find good parents for the seed. Now I understand that V1 and V5 cannot be good parents together because they are very similar. They are like a cousin. If I want to find the parents, maybe I cross V5 from here with V6 or 7 from here. These two are very different from each other. They are totally 2 different groups. This is group 1 and this is group 2. Okay, and when you have this, there is also one line here. This line here. This line show you what is the similarities that, for example, here is 90%, 80%, 70% until, for example, 0. So you can see that, okay, this one, for example, I come here, go, these two are 80% similar. These two are 70% similar. This group and this group are, for example, 40% similar. This is what we call cluster analysis. So cluster analysis, I have a group of samples or varieties or genotypes or students. You have a group of things. You measure some variables among them, and you want to group these samples, these varieties, these students, these animals, whatever into distinct group, that the one which is similar go to one group, and each group should be different from the next group. So, and you can see here also for analysis, I am using all the traits at the same time: yield, plant height, number of fruit, fruit size, everything. So cluster analysis also is a multivariate analysis. We use everything at the same time together. So this is cluster analysis, can be very helpful, especially for dividing the students into the different group space. For example, you have now you have different courses you get. I can get the marks for all of the courses you passed so far using the mark, and after that divide you in different groups. The students who perform, for example, well in science will go to one group. The students who did better in education, they go to one group. The students perform better in nothing, they go to one group. So I can do this. So if I can do this, later I can say that, okay, these students are good for science, better to do FIP in science project. These students are good for education sciences, better to do some education. So this is the purpose of this. And in agriculture, we use this many times to find a parents to cross together to make a better children. So this is one of the techniques that in plant breeding we use a lot to find parents. So when we go to PCA, in PCA, imagine that I have a data like this. Okay, this is my data in an X and Y axis. This is the data I have. So you can see this is in this direction, this is the highest, for example, and this is the lowest. So this is my one data, maximum to minimum. It is data one. For example, this can be your number of fruits. Another direction is from here to here. Data two, or variable. I don't call it data, let me call it variable. Variable two. And this is variable one. So when you look at these, which variable gives me more information? Variable 2 gives me more information, or variable 1 gives me more information? Any
Variable
idea? Variable
2.
Variable 2 gives me more information. Therefore, I can put one line in the middle here, for example. After that, forget about variable 1 and put all my data in this line. So this one will come here, this one will come here, this one will come, this one, this one, this one. That one is already on the line. This one here, this one here, this is here already, this one, and this one. Okay, so now you know what I did? My data was 2 dimension. I make it 1 dimension. Here is very easy. I understand that this one and this one are very different. So in these 2 data, V2 has more variation than V1. Okay, so now imagine that you collected, in this case, for example, 1, 2, 3, 4, 5, meaning to say you have 5 directions among your data. Okay, 5 different directions of data. Okay, what PCA does, PCA come and calculate some things, we call it as a principal component. We call it PC. Okay, so if I have 5 variables, maximum I can have 5 PC. Okay, so in this PC, we said that PC1, for example, after that PC2, PC3, so on and so forth. So always, for example, and this is percent of variation covered. If you use PC1, how much of total variation? Okay, of this total, okay, now here, for example, of the total variation, V2 is 70%, V1 is 30%. So if I forget about V1, still I have 70% of total variation. So why should I measure V1? I just measure V2. So imagine here I have not one, sometimes we have tens, 20, 30 of these variables. So what we do, we can change them to the PC. This is a calculation that from these variables, I calculate the PC. Always PC1 is bigger than PC2, PC2 is bigger than PC3, so on and so forth. So for example, there is here in the table, when you look at the analysis, you always see they call it variation or variance. Okay, that meaning to say how much of total variation in the data is covered by PC1. For example, they say PC1 is 65%, PC2 is 20%, PC3 is 11%, PC4 is, okay, for example, 6%. Okay, how much is total? The total should be 100%. Okay, so 65, 75, 85, 95. Okay, this one cannot be 20. Let I change it to, for example, I change it to, for example, 15. This one I change it to 10, for example. Okay, so 65, 75, 80, 90, 96. Maybe PC 5 is 3%, PC 6 is 0.8%, PC 7 is 0.2%. I have 7 PC, for example. Total became 100%. So now it says that if you want to look at the variation in the data, you only look at the first 3. Forget about the rest, because the first 3 gives you 65 plus 15 is how much? 80, 90. 90% of your variation is in these 3 PC. So don't forget about them. So imagine I have a lot of variables. From all of these variables, I can have these 3 PC, and these 3 PC explain 90% of everything in these variables. 90% of variation in all these variables are done by these 3 first PC. Sometimes even the people say these 3 first PC, they say, okay, 2 is enough. 2 give me 80%. So I just say, okay, instead of measuring these 7 variables, I just measure the variables for PC1 and variables for PC2. For example, these 2 are under PC1, this 2 is under PC2, example. So next time, I don't need to get data from these variables anymore. I only get data from these 4, and I know that this 4 gives me 80% of all variations. So therefore, it is very, and then we want to make a graph PCA most of the time show by graph, whether 2-dimension graph or 3-dimension graph. If 3-dimension graph, I am using the first 3 PC. If 2-dimension graph, I'm using the first 2 PC. So let's say I put it like this. Now this is PC and PC. For example, this is a bigger one, I call it PC1. This is a smaller one, I call it PC2. So after that, I put what I put there? My varieties. So again, here, for example, this is variety 1, this is variety 5, this is variety 3, variety 4, variety maybe 2. Here are variety 6, variety 7, variety 8, variety 9, and variety 10. So they drop, all of them are 1 point on this graph. So again, you can see, these 2 PC divide my variables into 3 groups. This is 1 group, this is 1 group, and this is 1 group. So you can see, and most of them are different in PC1. You can see PC1 still has a bigger variation, 65%. This PC is only 15%. So that's why, for example, this one and this one, this is the variation covered. Here, the variation is covered from here to here. So 65% is PC1, 15 is PC2. So therefore, using only these 2 PC, I can divide my varieties into 3 groups. Why should I use all these many variables to say which variety is similar to each other? I do from these variables, I calculate the PCs. After that, okay, when PCA analysis is good? When that your first 2-3 PCs are 70% and above, meaning to say the first 3 PC are 70% and above variation. This is a good PCA analysis. But if your PC1 is, for example, 20%, your PC2 is 15%, your PC3 is 10%, PC4 is 8%, another one is 7%. So if like this, my PCA analysis is no useful. Why? Because my first PC is only 45%. Still 55% is left. So this is not a good analysis, meaning to say PCA here is not good. So what can I do? I can go back to my data and I look for these variables that they are highly correlated. Correlation exactly that they are very dependent to each other. If these variables and these variables, these 2, are very dependent to each other, I need to remove one of them. Because when they are very similar, why should I have 2? I just have 1. So this is one of the way we can do. This is PCA. What is factor analysis? Factor analysis is exactly like a PCA. No difference. The only difference is what type of data you use. PCA, you use quantitative data, the data that come from a real measurements. In factor analysis, you get the data from questionnaires. What is this? Your variables are mainly educational, maybe psychology and these kind of variables. This is very into social sciences, factor analysis. For biological sciences, most of the time we use PCA. For education, social science, psychology, this one we use factor analysis. And because some of you maybe wants to do research in what is this? In education science, maybe you can use factor analysis. So in factor analysis, So what I do, for example, again, I have variable 1 is, for example, what is your sex, male or female or gender. Variable 2 is, for example, how old are you, age. Variable 3 is, do you smoke. Variable 4, for example, are you satisfied with life? So I have different variables. After that, I want to group these variables into different factors. So for example, I say variable 5, variable 6. Maybe I say, okay, variable 3, 4, and 5. These three examples are related to anxiety. These three, this one, and this one, are related to health science. To health of the individual. So you say, okay, I can divide my variables into two factors. One factor is mental health, for example. Another factor that this is the 3-1, or for example, physiological phase. Okay, so I have 6 variables. What I can divide my variables into 2 factors. This is, we call it factor 1. This one we call it factor 2. So now I can divide my individual samples. Here was variety 1, variety 2, variety 3. Maybe here you have a student 1, a student 2, a student 3, a student 4, a student 5, so on and so forth. Now you are able to divide the student. Which group of students are more physiological health is higher? What group of a student has a mental health is higher? So you never measure mental health and physiological health. Your question about sex, age, smoking, happy with life or not, I don't know, do you go to cinema? How often do you go to cinema? Your question is like this. But when you group them into different factors, you can see, okay, this anything related to health is come to, for example, one group. So I call it, for example, mental health. The other ones go to another factor. So this is the researcher who is who is an expert, can decide what is factor 1 name. Is it based on the research? What is factor 2? But the basic is same. Again, I have some samples and I collect some variables on the samples. First, I divide my variables into a smaller number of factors. Again, this factor 1, for example, is 60% of total variation. Factor 2 is maybe 30% of total variation. If you have a lot of other things here, variable 7 until variable 20. Okay, maybe they go to factor 3, factor 4, factor 5, for example. So you said that these 13 variables are all useless. Why? Because all of them are 10% variation in my samples. 90% of variables are these 6, which is divided to 2 groups, mental health, physiological health. Then I can group my students into 2 groups to understand that how these students are divided, which of them have a problem mentally, which of them have a physiological health problem. So you can find. So this is exactly like a PCA, but in here I will have most of my data come from a type of questionnaires. So this is a questionnaire data. This is more in educational sciences, but the basic is same. And don't try to calculate. I mean, you can calculate, even I know how to calculate PCA manually, but nowadays we don't do it because it is very time consuming. So what we do, we always use software. SPSS, for example, very famous to use this factor analysis. Okay, you can use all of this analysis I talk with SPSS. You can do all of them with SAS. They will give you all of this information. They will give you the graph at the end to divide the things. So this is the purpose. These three, cluster analysis, PCA, and factor analysis, these three, we call them dimension reduction analysis. So you want to reduce the dimension of your variation and only keep the important dimensions. So if you measure 20 variables, you have 20 dimensions. You want to reduce these dimensions of 20 into 3, but still cover more than 70% of the total variation. If you can do this, your PCA is very good, your factor analysis is very good. In cluster analysis, we are very keen to divide my samples into different distinct groups, that how I can put these varieties into different groups. This is about cluster analysis, and cluster analysis has many different techniques. Okay, but remember that, for example, when I was doing my PhD, I want to select for parents. I have data from phenotype and also DNA. So for both of them, I use cluster analysis and PCA to show what is the variations. Okay, so maybe when you are presenting, maybe I show some of the analysis for my thesis that I did, then you see how we divide the things into different groups. But the analysis was PCA and cluster analysis. I didn't use factor analysis because my study was not in educational base. But factor analysis is the same as PCA for data coming from social sciences studies. So because those data are mainly labels, they are labels. But remember, when you want to do factor analysis, you cannot use alphabet in SPSS, for example. You cannot write yes, no. You have to give number to them. Yes is 1, no is 2, to be able to do factor analysis. If you use alphabet as a name, you are not able to, the software doesn't do factor analysis for you. And last things to say is about regression analysis. What is regression? In regression analysis, I always want to do something. Last time I mentioned to you about dependent variable and independent variable. Correct? I have a dependent variable and independent variable. This is V, not R. And independent variable. Okay, we mentioned that dependent variable is like yield, for example. Independent variable is like time, like treatment, for example, you use. So many other things. Yield and other things, for example. Okay, what is regression analysis? Regression analysis is I estimate dependent variable using independent variable. Okay, just one example I want to do. For example, I want to look at the growth of corn or any other plant you want to talk about. Okay, what I do, this is, for example, let's say weight, plant weight, and this is time. So this is days after planting, days after planting, or some people call it day after sowing. So this is day 0. After that, day 5, I go and get sample. Day 15, day 25, day 35, day 45, so on and so forth. Okay, then I say that, okay, in day 5, my weight was this much here. In day 15, my weight was here. In day 25, my weight was here. In day 35, my weight was here. In day 45, my date was here. So maybe I go another day 55, it was here. Because my plant maybe is losing leaf here. If the leaf drop, so you lose the weight, 55. Okay, so if now somebody asks you, I have planted corn, and now I am at day 20. How much my plant should weigh in normal situation? I want to know that. I have planted corn. I feel that my corn farm has a problem. I come and ask, I am at day 20 here. At this day, how many gram one plant should weigh? You cannot answer me. Why? Because you do not have a data for here. There is no data for day 20. So what we do? What we do is we do regression analysis. In this regression analysis, I will go one line that it is nearest to all of these points. The nearest, I don't connect them. I go a line very near to them. So this line, we call it regression line. When I have this line, what happening when I have this line, I can understand that any day you tell to me, day 30, I say, okay, day 30 is here, I go up, cut here, I go this way. Okay, day 30, your plant should be this much. So you can understand. And because this is a line has a equation. You have a line equation. For example, for this one go up and after a while go down. So this is plant height or plant weight, sorry, is equal to A plus BX plus CX2. Okay, so what is X? X is time. This is time. Time and time to the power of 2. What is this A, B, and C? These 3, we call it regression constant. They are numbers that you find them by calculations. For example, your result will be 0.5 plus 1.2 x plus or minus 0.781 x2. This became your plant weight. So what happening? Any day I want to find, I can find from this equation. I even don't need to draw this. From this equation, you say to me day 5. Okay, I put 5 here. So 0.5 plus 1.2 times 5 minus this value times 5 to the power of 225. So based on this, I calculate the plant height. This is, we call it regression analysis. I could estimate plant weight using time. Time is my independent variable. Plant weight is my dependent variable. So I measure dependent variable using independent variable. I estimate. This is, we call it simple regression. You say, do we have other than simple regression? Yes, we have another one. I don't want you to cover that, but we have another one. We call it multiple regression. In multiple regression, I have more than one independent variable. For example, I have time and day temperature. So I guess plant weight using time and temperature. So temperature also is independent. So that is multiple. Why? Because I have more than one independent variable. I have 2, 3, 4 independent variables. So that is multiple regression. I don't want you to go to that because that one will have a selection of independent variables and very complicated will be. Okay, so you just do this one, understand what is regression analysis, simple regression analysis. This is simple regression analysis. Okay, but if I want to change this PW, for example, plant weight, is a qualitative data. For example, it is satisfaction by, for example, rat size. Now you want to get some data from rat. You want to understand that if my rat eat this much of food, what is the size of the rat? Okay, what I want to say to you that here, this data is qualitative. You can do the same data analysis for this data is quantitative. You can do the same study for qualitative data also. The qualitative one, we call it logistic regression. So simple regression analysis, we do it for quantitative one. Logistic regression, we do it for qualitative one. What is the difference? The difference is only one kind of data you have. The first one is data coming from a quantitative variables, means you measure it, plant weight. You measure plant weight by balance. But logistic regression is guessing or estimating a qualitative variables like weight, like satisfaction from life, whatever. That one we call it logistic regression. So this one is all, and this regression is very good. Many of the students who do FIP in our department can do regression analysis. They can do what is this? They can do multivariate analysis of variance. These two, many of the students can do. Why they don't? Because they don't know how to do it. Many of them in education science, they can do this factor analysis. Factor analysis, if you do factor analysis, you have a lot of things to discuss about it. Okay, so, but many student doesn't do because they don't know what is this and how to do it and this. So I hope this semester because this has mark also for your class, so a group of you sit down together and try to understand these subjects better. After that, write, I don't want a very lengthy report, write a good report that the basic is there. I don't want you to go also very details, okay? Because now you are not at that level. First, you need to learn the basics of these techniques. Okay, of course, that basic is not good for analysis of any data. Why? Because there are a lot of tricks here and there, But when you know the basics, you can go and get advice from one person who knows. After that, through the time, you learn and learn and learn. So here, I don't want you to be very detailed. What I want from you is you get a data, give some introduction. What is this? Who developed it? Some history, some basics. If there is any assumptions, what is the assumption? And the best is after this, you give a real example that this is the data we did PCA analysis and this is the result, and try to explain the result. If you can do this, it is very, very useful for you. And if you have a good thesis, good data collection for your FIP, you can easily use these complicated techniques and produce a very good paper. If you do only ANOVA, it is no publication will publish your paper because this is very simple. But if you do ANOVA and also talk about MANOVA, meaning to say you talk about everything together, maybe you can publish your data because that is more complicated. So this is the basic of these 5 assignments I'm giving to you. Multivariate analysis of variance. It is like an ANOVA, but we have everything together. Every variables I measure together. Cluster analysis. The aim of the cluster analysis is grouping the individuals or varieties or genotype, whatever, into different groups using the data collected. Here, in cluster, I don't want to say which variety is good, which variety is bad, which yield is high, which yield is low. This is not important. What is important is which variety are very similar together. Which varieties are very different from each other. This is important. So in cluster analysis. In PCA and factor analysis, what is important is that I have collected a lot of variables. But when I want to discuss about my samples, instead of discussing 20 variables one by one, and this is high, this is low, this is this, this is that, I will change my data into a new things, we call it principal components. And then I can use 2-3 principal components to talk about everything, because this principal component, if the analysis is good, can cover most of the variation in all of the data collected. So I can, for example, like here, I can then use PC1 and PC2. I draw PC1 and PC2. After that, plot my varieties. After that, I can say, okay, this is one group, this is one group, this is one group. So my varieties fall into 3 groups. Later, I can say, okay, variety 1 and variety 5 are different from variety 3, variety 2, and variety 4, mainly on PC1, because in PC2, they are very near, side by side, not very far from up to bottom. From left to right, they are far. So I understand that they are different in PC1. Then in the analysis tell to me what is which of these variables are PC1, inside PC1. So you can understand, okay, this group and this group are different because of these variables. So this is very easy and very nice with proof. You can discuss about differences among these varieties or genotypes or students or whatever you want to group inside. Remember again, here the objectives in cluster analysis, PCA, and factor analysis is not saying who is the best. The aim is differences, that how can I group them in different groups, and these groups became different from each other. For example, in UPSI, I gather the data. After that, my data from the students, Then I can group the students into 4 groups, for example. Became Malay groups, Chinese students, Indian students, and Middle Eastern. You didn't get a data about who is Malay, who is Middle Eastern, who is this. You get the data about height, weight, age, and these things, huh? Then, because the Malay students are more from same genetic, they are, for example, similar height, similar weight, so they go to one group. You say, oh, okay, oh, all of the people in this group are look like each other. They look at Malay. So, oh, okay, this group is for Malay students. This group, oh, they are look like, for example, same characteristic like Chinese people. So mainly they are Chinese in this group. So you collect different variables, but you group them into different group based on their race. So this is very good analysis that we can do. PCA and factor analysis also is very similar, but factor analysis is for social sciences. Here, my PC call factor. In PCA, each of them call PC. Here we call them factor. And this factor, I put my variables I collected into different factors. Then I say, okay, these factors has this component inside. These components are mainly for mental health. So then I can put which students will go to this group, or these students have a good mental health. Which student go to this group, they have better physiological health. So this is how we discuss. And for regression analysis, the aim is estimating one dependent variable. This is dependent variable using independent variable. So how we can do this? We can use this by regression analysis. And we have many different regression. The regression, for example, this is linear, go up. This is linear again, go down. This is exponential, go and stop. This is sigmoid. This is quadratic. This is cubic. So how we find these things? Based on what line you will have. This line I write here, this equation a plus bx plus cx2, this one is for this line. If my result became like this, I understand my variation looks like this. Means go up until a certain point, after that slowly go down. If became like this, means go up until a certain point, and after that stop, no change, no go down, no go up. So how can I find these things? These are, we call it regression. So how do I do this? How do I do this is I will test all the line. For example, for this linear one, for example, this one is a plus bx. A plus bx is my linear regression for the first one. The second one is a minus bx. This is the regression which goes down. This is the regression that goes up. The difference is only this sign. So you can see this became positive, this became negative, go down, go up. So I have to say to software what I want. After the software calculate for me this ABC. Then, and also the software tell to me how good is my regression. My regression is good or not. If my data like this, can I use linear regression? Yes, you can use line like this. This became your line. But this line is not as good as the black line. Why? Because the black line is much nearer to the real points. That's why there is some things in regression, we call it R square. Higher R square is better. For example, for this one, R square is 0.9. For this one, R squared is 0.4. So, meaning to say, this one is 90% near to real. This one is 40% real to near. So, then you understand, okay, this is my regression line. When you understand which line you have, you find ABC, and based on this ABC, you can use it anywhere. Anywhere you want to find plant weight for the corn, you can put it in this equation. And this one is time. Okay, that's all. I can put it here, and I find where is the corn on this graph. That's all about these three assignments. So I talk too much. I hope you understand this. And go and do some study. Please understand that you have to spend some time on this. You cannot just download one paper and you feel that I'm good at this. No, you have to read a little bit more. And the best is don't read much paper first, because paper, they use it. They don't explain. The best is you try to find book chapters. Book chapter, mainly they discuss the basics. In paper, they don't discuss the basics. They use it to analyze some data. So they don't talk about the basics. You can use the paper as an example of analysis, but for the basics, the best is you try to find the information from the book. All right, guys, thank you for today. If there is no question, it's enough.
Okay, sir.
No,
Doctor.
All right.
thank you.
Okay. All right, everybody. I hope you
Thank you,
understand.
Doctor.
All right. Have a
Thank
good
you,
day.
Doctor.
And
Thank you.
thank you. Thank you, everybody. Have a good day. Goodbye.